Good morning, and thank you for joining us. I'm Jackie Castle, Chief Technology Officer at the Aerospace Technology Institute, and today's webinar is part of Net Zero Week 2025. So this is the UK's official National Awareness Week and the biggest net zero conference. You will discover more about the work that we've got underway to decarbonise aviation and hear how aircraft technologies can make a big contribution to reduce emissions and deliver a more sustainable flight. You'll hear from members of the ATI technology team, and I'm very excited to say that we'll have Simon Davies, the Chief Test Pilot at Vertical Aerospace, joining us a little later on. So you'll also have the opportunity to ask questions during our Q&A. So if you're not familiar with the ATI, we create the technology strategy for the UK aerospace sector, and we fund world-class research and development working alongside government and industry to transform aerospace through technology and innovation. And since 2014, we've invested 3.6 billion of joint government and industry funding in over 400 transformational aerospace projects, delivering economic benefits across the nations and regions of the UK. In 2024, the aerospace industry turned over £35 billion worth of work, contributing 13.6 billion in GVA. So the sector is one of 8 frontier industries highlighted as key to UK growth in the recent published industrial strategy, and it's also announced a 10-year commitment to improve funding stability for public R&D investments. So it's really a fantastic endorsement for the excellent research happening through the ATI programme, and will give security for businesses to accelerate and deliver on the strategic ambition, as well as being a catalyst to attract further private investment. So we're nearly halfway through a critical decade for the aerospace sector, with key decisions about which technologies will make it onto the next generation of aircraft likely to be taken in the next 5 years. And to stand the best chance of winning future work and maximise technology's contribution to reducing emissions, organisations must develop and mature those new technologies, make them cost competitive and able to be manufactured at high production rates to meet the demand for new aircraft. So on this webinar, we'd like to introduce you to the technologies being developed today for the benefits of sustainability and the UK economy tomorrow. You will hear what's being done to make the aircraft even more fuel efficient, followed by a deep dive of the importance of manufacturing with advanced materials to realise more sustainable aircraft. And this is rounded off with some examples of some of the most revolutionary research looking at aircraft which could fly without producing any emissions at all. So please sit back and enjoy the presentations, and I look forward to taking your questions later. Thank you. And I'm going to hand to Tom, who will start talking about efficiencies. Thank you, Tom.
Thanks, Jackie. So, morning, everyone. I'm Tom Halhead. I'm the Head of Technology for Advanced Systems and Propulsion at the ATI, and over the next 7 minutes or so, I'm going to try and take you through the why the development of ultra-efficient aircraft technologies are a win-win. So to set a little bit of context, really, we've got a sector which is trying to grow, and the only way we can do that in a sustainable manner is by delivering the technologies that allow us to increase efficiency over the current precedent. The reason we call this a win-win is because a lot of the drivers that come with increasing efficiency also have other benefits, namely the reduction in environmental impact that we see as a sector, but also critically its ability to reduce operating costs as well, particularly when driven in the right way. But it's a cumulative gain as well. So we invent these technologies on a particular platform, but then they will be adapted, scaled, etc. to other, and we'll build upon those. And Dave will touch on that later when we talk to some of the zero carbon aircraft in the longer term, which will inherit some of these technological developments that we're doing at the moment on next generation. But the key point to get across really is that scalability remains a huge challenge. So at the moment, if we look at the electrical grid, which ultimately is going to be responsible for producing a lot of the fuel that we'll use into the future, there's only about 20% of the total energy demand of the country comes from electricity at the moment. So we need the grid to scale, and that to get to a point where we can deliver fuel to the likes of Heathrow. And for calibration, at the moment, Heathrow gets through about 20 million litres of Jet A1 per day. Multiply that by the calorific value of the fuel, and you get a sense of the demand that we're placing in terms of energy consumption into the future. So how do we reduce that? Well, if we look at what the art of the possible is, sounds wonderful. An electrical vehicle at the moment has a grid to shaft power efficiency of about 80%. Why can't we do that in aerospace? Well, the challenge in aerospace is always been one of trying to produce sufficiently light solutions. This is where a vicious circle can occur, because fundamentally the energy storage system on an electric vehicle is a battery generally, and the battery power density at the moment is about an order of magnitude lower than we get from a typical aviation fuel. What that means is that when we try and put those on a large aircraft, that aircraft, the mass, the installed thrust, the wing area of that aircraft trades develops in a way that currently doesn't work for a large aircraft. So we need things in between. And where you look at where we are at the moment, there's a systems engineering activity to do, essentially, that we're right at the heart of the ATI, of saying, where does the fuel come from? How efficient is the production of that fuel? And how efficiently can we turn that fuel into power for the aircraft? Alongside trying to bake in some of these efficiency improvements. And you'll see there that we've got conversion efficiencies when we're trying to make fuel of the order of 40 to 50%. Again, when we're trying to combust that fuel and turn it into thrust, 30 to 40%. You see, we're a long way away from other sectors and other areas. So what we'll take you through over the next few slides is some of the technologies that's being done in different timescales to try and deliver on some of that ambition. So what are we good at, especially in the UK? Engines and wings. Critically, these are the things that make particularly big differences to aircraft efficiency. So the next couple of slides are going to look across a range of timescales. So what are we doing at the moment? There's obviously a lot of focus on future technology and more disruptive architectures, but there's an awful lot of technology that's been fed into the fleet to deliver incremental improvements. So on the engine side, we're seeing ongoing performance enhancement. What's driving that? Advances in materials, advances in techniques to increase efficiency, keep the engines on wing longer, support performance retention through things like enhanced compressor washing. So there's an awful lot of technology going into these areas that perhaps doesn't get the press it deserves at times. But also we're starting to see all of the manufacturers demonstrate compatibility with the fuels of the future, notably SAF. And many of the technologies that we'll talk to in a second on the next generation have applicability to current fleet as well. So the developments that we're funding on future engines are also finding their way to improve the performance of current fleet. But that'll only get us so far. And for the next generation of aircraft, critically the next gen single aisle, which we're expecting to launch in the mid-2030s, we're looking at fundamentally different engine architecture from the majority of direct drive engines that are out in the market today. At the moment, that could take one of two forms, really. The general sense is that either a geared turbofan or an open fan architecture would be the way to go. And the way those are delivering their efficiency gains is through improved propulsive efficiency. That's trying to shift more air slower, and increased thermal efficiency. So that's fundamentally running the core of the engine hotter and at higher pressures in smaller cores and essentially it's the product of those two things together that give the efficiency gain. We're expecting those engines to deliver around about 10% improvement in their own, which will couple together with Airframe technologies that will be designed alongside them. But also we expect those engines to have an increasing level of electrical content, which plays to that theme I mentioned on the previous slide. Fundamentally, electrical systems have got very, very good power conversion efficiency as long as they can be designed in a lightweight manner. So increasingly in the program, we're seeing more and more electrical technology, more and more energy storage technology, and that's applicable to engine use. But the critical thing there is the transfer efficiency, and that ultimately will dictate the level of hybridization that we see on the next generation of engines. And then finally, on the engine side, with an eye well into the future, we're starting to see some really interesting engine concepts too coming through. So notably Pratt & Whitney's HiSight engine, but this is actually looking at where you have cryogens on board, like hydrogen. Can you use some of the properties of that cryogenic fluid, with a more radical engine design to dramatically improve efficiency, but also reduce some of the other emissions, notably NOx, that are associated with some of the current combustion technologies. Click on, Nathan. Thanks. And so in parallel, what else can we do on the aircraft? Well, our three major themes on the aircraft, if you like, are the airframes, the structures, propulsion, and systems. So on current fleet, what we're looking at there is there are drag reduction opportunities, but critically there are midlife upgrades, notably the provision of interiors. And what we're seeing is a lot of the materials technology that has been developed for airframe structural use, particularly composites, being applied to interiors, which make up a significant proportion of the aircraft weight. Those get refreshed every 5 to 10 years. So over the lifetime of an airframe, you can achieve significant mass reduction. That's just one example. We also see cabin systems being reconfigured to reflect more communication demand, for example. And again, those things can be adapted to give efficiency gain. And similarly, we also look to the future in terms of this next gen single aisle aircraft and beyond. So in the short term, we're looking at increasing composites use, some quite disruptive wing technology, so that's higher aspect ratio wings, and the technologies that will allow those to be operated at conventional airports, things like folding wingtips, and critically more sustainable aircraft operations too. So minimizing fuel burn on ground, in the air through advanced operation, and flight path optimization. That comes with a lot of software technology, and we're looking outside the sector for assistance in doing that. And then finally, we've got the more radical aircraft architectures coming through, notably the likes of Jet Zero's blending wing body concept, and over time that's being touted to deliver up to 50% efficiency improvements as the ultimate aim. So I'll wrap up there, but hopefully that's an overview of some of the things that we're looking at in terms of the airframes, propulsion, and systems aspects of the technology portfolio, all of which are delivering near-term and long-term technology or efficiency benefit. I'll hand over to Alex now, who will talk through some of the advanced manufacturing elements that enable those.
Thank you very much, Tom. So I'm going to talk you through gearing up the supply chain through advanced manufacturing. My name's Alex Hickson. I'm head of technology for structures, manufacturing and materials. So what is the UK good at? The UK is world leader in design, development, manufacturing and test capabilities across aerostructures, propulsion and systems. That offers huge opportunities for the UK. It also holds the enviable position of having design authority on wing, gas turbines and landing gear, with test facilities to validate these new designs and technologies. The combination of this with the ATI's portfolio of differentiating technology developments in materials and manufacturing that are embedded in the UK primes, supply chain, academia and research technology organisations enables the translation of innovation into lighter weight, more efficient, cost competitive products and services that will be made and supplied in the UK. So looking to how those investments are spread across the sector. So we have advanced technologies that broadly sit into three categories. There are others, but this is where the bulk of the spending goes, which is looking at composite technologies, metallics technologies and assembly. To bring some of these opportunities to life, where ATI investments will unlock and also help focus some areas of the ATI portfolio. We've looked at these in specific detail of what we're investing in and where the gaps are and things need to address. We move to the next slide. Composites uptake in commercial aircraft has been an upward trajectory since its introduction more than 80 years ago. To me, more than 25% of modern large civil platforms and 50% of or more of the long-range aircraft. Why is this? Put simply, weight matters. Using the ATI's fixed trade calculator, which is free and open for all to use, this enables interested parties and potential applicants to the ATI program to calculate the benefits of technologies at a whole aircraft level. Composite technologies enable weight reduction, not just through lower density, higher specific strength or stiffness materials over metallic materials, but also through more integrated structures, reducing parts count and fasteners. In turn, they can also provide benefits in aerodynamic performance, reduce assembly time, and open opportunities in more radical engineering and assembly concepts for further aircraft performance benefits. Composite materials and their advanced manufacturing technologies are critical for the next generation of ultra-efficient and zero-carbon aircraft. The advanced manufacturing technologies are required across the structured propulsion systems for converting these new material formats and formulations into aircraft products with minimal energy and material waste into near net or net shape products right first time and at a competitive price. That's key to the UK delivering on the benefits of these technologies whilst also delivering at higher rates. Aircraft today can be built at the order of 60 aircraft a month, but aircraft manufacturers are looking to go upwards of this to 75 to even 100 aircraft per month, which means complete transition in the technologies we manufacture aircraft today. There's a whole range of ways that this will be delivered across the sector. The key is that the technologies have to be looked at across from the OEMs through the supply chain, through the tiers, use of SMEs, material manufacturers, but also tech providers who are providing the tools, equipment, and integration of these technologies. The cumulative value of composite components for future ultra-efficient aircraft wings is will amount to over $80 billion by 2050. This value should only be captured with the engagement, investment, and development across all levels of the supply chain. There are great examples of innovation coming from the small and medium-sized companies such as ICOMAT with their rapid toe shear composites, offering weight savings in some use cases of over 30%. To organizations like Loop Technology that are innovating the equipment and systems for depositing composite materials at high rates for large structures in the open access research centres such as the National Composite Centre and Advanced Manufacturing Research Centre of the High Value Manufacturing Catapult. We move to the next slide. There's an opportunity to deliver greater benefits on aircraft and economic impact for the UK through targeting innovation across the value chain. We often focus on the technologies for manufacturing the product. As you can see here from the picture, the UK can enable aircraft and equipment manufacturers to achieve greater performance in service and in current and future factories to enable a supply chain that delivers world-class performance, making high-rate products right first time with digital passports and the lowest carbon footprint. So looking at capturing opportunities through having design capabilities here, the materials manufacturing capability here, making the products, inspecting them and assembling them into the final deliverable product, but also looking at the recycling end of life. That's across the materials. The moment unlocking that is about joining up the sectors and not just thinking in isolation about the aerospace sector. We move to the next slide. Some in-depth work has been done around the composites in aerospace, looking at a market spotlight where we assess the portfolio, where the gaps and opportunities are, and how we can bring the capabilities that are required for these next generation aircraft into the UK and with a capable supply chain able to win this future work. For more details, please go online, take a look and look at how you can engage to see how we can generate the roadmaps and strategy, and then through our programme fund the delivery of these technologies for the UK to be in best position to deliver the net zero aircraft of the future. At this point, I hand over to Dave.
Thanks, Alex. And good morning, everybody. My name's Dave Debney. I'm the Head of Technology for Whole Aircraft at the ATI. And today I'm going to talk to you about some of the work that we're doing in the zero carbon space. There are lots of options that you can use to fly an aircraft with zero carbon, but we're going to focus on two areas in particular today where the ATI has active research programs. Those are hydrogen and batteries. So firstly, I'd like to talk about hydrogen. We see this as a really promising zero carbon energy source. What we mean by zero carbon is zero carbon coming out of the tailpipe of the aircraft. The ATI led a project called Fly Zero that researched all the different zero carbon options and concluded that hydrogen was the most promising, scalable zero carbon option. What we mean by scalable is the ability to scale up to large and long distance aircraft. The three aircraft on the screen are some concepts that were generated as part of this study. The aircraft on the left is a regional aircraft, so it's about 70 passengers with a fuel cell powertrain. The aircraft in the middle and on the right, in the middle is a single aisle aircraft powered by hydrogen gas turbines, and on the right is a large wide-body aircraft. Our studies showed that this aircraft could have a range of up to 5,250 nautical miles. That's approximately halfway around the world. This is important because that would cover up to 90% of existing flights. And ultimately, that's the kind of impact that you need to have if you're going to have both a major economic but also a sustainability impact. The reality of making hydrogen work is that it's a huge technology challenge. We've seen recently that some of the market timescales for hydrogen aircraft have moved to the right, but that doesn't mean there aren't things that we can do now. So the ATI's approach is to invest in what we call technology bricks. These are some of the critical enablers that we're going to need to enable the potential of hydrogen flight in the future. The majority of hydrogen systems today are developed for spacecraft. So they tend to be lightweight, but they also have very low life. So things like valves and pumps might only last for 7 or 8 minutes. For a commercial aircraft, you'd need them to last potentially 5 years to 10 years on the aircraft in service. That's a huge challenge in itself, especially when you're using liquid hydrogen, which all of the concept aircraft shown here do, at minus 253 degrees centigrade. Hydrogen storage is another critical technology. Because the hydrogen fuel is very light, but the tank is quite big and therefore heavy, finding ways to make the storage as light as possible makes a huge difference to the capability that you can achieve with the aircraft. I've not shown gas turbines on our technology brick page here. That's because it's actually fairly routine to burn hydrogen in gas turbines for energy generation purposes. Rolls-Royce in the UK have also run an aero engine on hydrogen, so we know that that can be done. It doesn't mean that it's not a technology challenge, but it's not at the same level as some of the challenges that I've shown here. On the fuel cell side, we have active research programs with companies like ZeroAvia, looking at fuel cells of the future and trying to increase the power density of those. We're also looking at cryogenic systems. So this is when you cool down the distribution cables for the electrical system and potentially the electric motors to get huge gains in efficiency, potentially as high as 99% efficient. Thermal management is the other critical enabler, because you have a very cold fuel that you need to get to ambient temperature at the point of use, but also potentially electrical systems generating significant amounts of heat, in some cases potentially megawatts of heat that you need to get rid of. So these are some of the key areas that solutions need to be developed now, such that we can feed them into the aircraft of the future. Moving on to the second topic of batteries, Tom touched on elements of this already. One of the biggest challenges with batteries is the amount of energy that you can store in them for a given amount of weight. Generally, we refer to this as specific energy. And at the moment, we're at about 200 watt-hours per kilogram. In the next 20 years or so, we think that we might get up to about 600. So what does that mean we can achieve? So working from right to left on the chart, we think in that timescale, you could get to major hybrid propulsion or smaller battery aircraft. You're looking at about 2 to 4 megawatts of power. For reference, 4 megawatts of power is approximately 20 Tesla Model 3 cars. This would enable you to provide part of the propulsion power using those batteries. That enables you to offset some of the system limitations that you have today, where the engines are required to generate almost all of the electrical power. The more electric aircraft in the middle are what we are seeing on things like the 787 aircraft already, but we expect this to become more prevalent on the next generation of aircraft. This is where more systems on the aircraft become electric. So rather than having so many things driven by hydraulic systems, you have more and more things on the aircraft being driven electrically. That means you need an elevated level of electrical power. But at this stage, we don't expect that electrical power to be used in a propulsion sense. Now, both the more electric aircraft and the hybrid propulsion are ultimately not zero carbon. But what they do provide is a route to continue the development of batteries to ultimately try and scale up the size of aircraft that can be purely battery powered. As I said, though, we don't think that a large commercial battery powered aircraft will be feasible for another couple of generations. So what can we do with batteries that we have today? Well, firstly, we can look at general aviation. So these are small aircraft, typically 2 to 4 people, and they have quite limited range. So you can buy an electric aircraft that's certified today from a company called Pipistrel. It will take about 2 people, approximately 100 miles. So it's a great start. And the cost of operating those aircraft has been demonstrated to be significantly lower than fossil fuel powered aircraft. But at the moment, it still remains limited. The other exciting area that we're actively researching are electric vertical takeoff and landing aircraft, otherwise known as eVTOLs. These aircraft use distributed electrical propulsion to enable vertical takeoff, but in the case of the picture shown there with vertical aerospace, they can transition to wingborne flight, which means that they're far more efficient in the cruise phase of the mission. This is a really exciting area that has the potential to disrupt some parts of the aerospace industry, and we're really pleased to be working with Vertical. Some of the key areas we've worked with them on are the rotor design, because it's quite unique, and also the battery design themselves. So that's a great segue into the next section of the presentation.
It's my real pleasure to introduce Simon Davies, who I'm now going to be talking with. He is Chief Test Pilot at Vertical Aerospace. He's brought over 3,500 hours of flight experience in more than 85 aircraft types to the forefront of electric aviation. His career has begun after studying physics and aeronautical engineering at the University of Cambridge before joining the Royal Air Force, where he served 16 years as a fast jet pilot, an instructor and an examiner. So at Vertical, Simon leads the VX4 flight test program, which is helping to pioneer this new era of clean, quiet air mobility. And he's personally flown the VX4 prototype through its most critical milestones, including the first 3 hovering flights and the recent first flight in airplane mode. So in May this year, the VX4 became the first ever UK designed, UK built electric aircraft of its kind to operate in open airspace, and the first entirely new class of commercial aircraft to do so from British soil in 40 years. So at the controls of that aircraft was Simon, Chief Test Pilot at Vertical Aerospace, and I'm really delighted to welcome him to our webinar today. So thank you, Simon.
Good morning, everyone, and thanks very much for having me. Thank you.
Absolute pleasure. Absolute pleasure. So we're going to have a bit of a fireside chat, and there are so many things that we could ask you, Simon, but let's start with when you were recently at the controls of Vertical's VX4 prototype as it made history on its first ever piloted wingborne flight of a winged eVTOL in European airspace. So what does it feel like to be flying at the very forefront of technology innovation?
Well, I mean, it's an extraordinary privilege, to be honest, to be at the forefront of electric aviation in such a groundbreaking kind of program, and also leading the way for British aerospace, the British aerospace industry as well. The aircraft we've flown actually in hover mode already. We've done about 30 flights in hover mode a bit earlier in the year. So this was our first flight in aeroplane mode. The aircraft's remarkably simple to fly for all the relative complexity of having 8 motors, 8 propellers, the forward propellers tilt. You've got conventional flying controls as well. The flight control computer sorts it all out for you. So the piloting task really very simple. It's very intuitive to fly. The biggest, so it's quiet and simple to fly, and it's great. The biggest sense I get is really one of huge pride in the team and the amount of work. You wouldn't, if you knew how hard it was to build airplanes, you'd never start. It's a huge amount of work. It takes real tenacity and dedication from a huge number of very talented people from around the world, not just in the UK. So it's a real honour to be in the cockpit, and everybody's. You can see it was 6 weeks ago the first wingborne flight. People are still smiling.
Mm-hmm. I can absolutely imagine it's very exciting even to see it from afar. So, I mean, you talked a little bit about the flight control system there. I mean, how does it differ from conventional systems and conventional aircraft?
So we've got miniaturized digital flight control computers from Honeywell, who also provide the flight deck avionics and the control law. And the control law is based very closely on the unified control law developed by UK MOD, NASA, Department of Defense over the past almost 40 years with the VARC carrier, the NASA equivalent, and then that was implemented on the F-35B. So unified flight controls give the pilot the same sense of operation in all flights, in all modes of flight. So you don't have a separate hover mode, you don't have a separate aeroplane mode. The controller always does something similar. When you move the stick, it always does something similar in all modes of flight. And this is the secret sauce really to making these quite complicated aircraft fly, but very simple. And it's also very good at it's all very highly error tolerant as well. So you can cope with either errors in your model or failures. Deals with that very effectively in all phases of flight.
That sounds
fantastic. And it also provides complete envelope protection for the pilot in design as well. So a really huge step forward in terms of application of digital flight controls into this class of aircraft.
I was going to say that you must be generating lots of data from all of the flight testing that you're doing at the moment. I mean, how does the sort of how do you measure success of that flight test program, and how are you using some of that data?
So success actually is generally that we either match real world performance to our predictions. That's the best result we could hope for, or we learn from the errors in the model and refine our models and modeling tools for next time. And that's probably the biggest takeaway, is that actually with this kind of digital aircraft,
building the tools to do your design and analysis is probably one of the biggest challenges. Once you can do things digitally, you can optimize very efficiently. So one thing we've learned is how to deal with that vast amount of data we generate on each flight. We're stress testers for flight test instrumentation and data radios and data management on board the aircraft. Managing the workflows to get that information to the right people in an actionable timescale is a real challenge. It's a real challenge. So we've built out those systems now to make it really efficient for people to access the data, to get actionable information into the right people's hands, to speed the rate of iteration through design and to improve the understanding of the aircraft in its real environment.
I think that's right. It's it's really great to see this sort of work happening in the UK, because that's going to develop engineers that will then take that learning and apply it more broadly across the aerospace sector as well. So I think that's really fantastic. I mean, for those that are less familiar with eVTOLs, can you tell us a little bit more about the aircraft and the sort of type of markets that this vehicle might serve?
Okay, so our product aircraft, the vertical VX4, the aim is to have an aircraft that can take off and land vertically. It cruises like an aeroplane with a wing, so it's very efficient in the cruise. It can carry 4 passengers plus a significant amount of baggage, about 100 kilometers dry tanks. 100 miles dry tanks. The aircraft has all electric motors, so direct drive, no gearboxes, and the launch markets. Our customers are typically a mix of scheduled airlines and companies that are looking at urban mobility, so moving intercity or intra-city. So airport feeder services are going to be some of the launch markets where you can use existing infrastructure. It kind of makes sense. But then also tourism flights, and then things like emergency medical services, either blue light response or point-to-point tasks that are tricky to do by road or perhaps prohibitively expensive to do with a helicopter. So my favorite example is air ambulance type stuff, where you've got point-to-point movements that happen reasonably regularly, but where time is quite critical. One of our customers is Iberojet, and they cite the route. There's an island called Formentera, just off Ibiza. The direct line between the two hospitals is less than 10 miles, but the journey can, because you've got to take a boat, it's busy in the summer, can take 2 hours to do patient transfers between the hospitals. So that kind of thing could easily be enabled relatively cheaply, by our aircraft, and that's the kind of thing that gets me really excited.
Yeah, no, that sounds fantastic. And so on the noise as well, it is how have you been able to look at sort of the noise levels? Are they as expected? Much? How would they compare to a helicopter?
The feedback we get from we're doing scientific analysis of our noise spectrum, both for the prototypes and for the production aircraft as well. But the feedback we get from our customers that have been to see us fly is that the character of the noise is quite different. It's a different. You don't get that whop that we all know from helicopters. It's more of a whooshing, buzzing sound. It's lower frequency. It's higher frequency than a helicopter, lower frequency than an airplane. So propellers spinning at hundreds rather than thousands of RPM. So the character is very different. And often in operation at Cotswold Airport at Kemble, what used to be RF Kemble, you really can't hear our aircraft over the noise from general aviation aircraft that are quite a lot further away. So it's really quite pleasing. Yeah. And in CTOL mode, in aeroplane mode, it really is very quiet. Not quite as quiet as on the video just now, but it is very, very quiet indeed.
Yeah, I'm sure that feature is going to really help with sort of different markets as well, isn't it? So that's interesting. So maybe just to sort of wrap up on the questions, but what are the most significant challenges test flying an eVTOL then compared to a fixed wing aircraft, with which you've had lots of experience of looking at your career history?
The biggest, there's quite a few. The regulatory environment is probably the biggest, actually, because there's so much novelty. It's a bit of helicopter, it's a bit of aeroplane, but it's really neither. So, finding our way through development and testing of the aircraft, and we're testing a full-scale prototype with a pilot on board at the moment. So we're doing that in conjunction with the UK CAA, and they set a really high bar for safety for us, but they're 100% on the journey with us. They're committed to making this happen too. And we've got the additional hurdle compared to, say, our US competitors. There's no experimental category in the UK. We have to go through the UK CAA permit to fly process, apply for flight conditions and a permit, and the regulator shares responsibilities for safety with us. And we see that as both a challenge and an opportunity. So it's harder in that we have to involve the CAA in our engineering and design and our operational safety case. But actually, we kind of see it as an opportunity as well. It's kind of like going through a mini type certification campaign. We're using the design organization, processes, approvals, the same people. We're interfacing with the same people at the CAA. So that's a huge challenge at the moment. Then coming up next for us is transition. The other question I get asked two questions: what's it like to fly? When are you doing transition? So we've done hovering flight. We've proved the aircraft's fundamentally safe in aeroplane mode. The next big hurdle is to join up the two at transition, and we're committing to doing that this year.
Mm-hmm. Okay, now that's fantastic. And I think what we'll do now is go to some general Q&A, and I'll have a little look at the questions that are coming through. And I think we'll be bringing back the other presenters as well to join in that Q&A. I mean, one of the questions that has come in was very linked to what you were just saying, Simon, about the UK regulatory environment. I mean, you sort of said it's a challenge and a benefit, but people are saying, does it disadvantage us sort of globally, compared to some of the eVTOL sort of developments maybe in the US that we understand are perhaps not targeting the same level of safety standard for those initial vehicles? I don't know if you've got any additional comment on that.
Well, we've said this very openly. We're entirely committed to the highest safety standards that are set by the UK CAA and EASA in SC-VTOL, and it helps us in a few ways. Actually, firstly, unlike in the US, we don't have to agree a case-by-case certification basis. We've got this openly published, really clear set of certification specs, or it's a special condition but equivalent to certification specs in SC-VTOL and the associated means of compliance. It's really open, it's clear, it's transparent, it's clear what we need to do to certify the aircraft. And then the 10 to the -9 safety standard we think is the right way ahead. It is more challenging, but it's going to give us, at the end of the road, is a product that we can export to any market in the world. We've got customers in 5 different regulatory jurisdictions. So that's really important to us as well. We have a flexible product we can use anywhere.
Yeah, absolutely. Okay, now that sounds great. It's really good to hear that you're working really closely with the CAA and are obviously clearing each of the test flights and everything anyway, aren't they, and working alongside you. I should say then that we're into the live Q&A now. So thank you, Simon, for the questions that we've had, and welcome back to everybody, like I said. So for people online, if you want to ask any questions to the team here, please type them into the Q&A, and then we can see those and they'll come through to us. Let me just check if there are any fresh ones at the moment. But otherwise, I was really going to ask to maybe go back to vertical at the minute and just ask about the flight test milestones ahead. You talked about transition. If you do that milestone, then what are the next sort of main steps and challenges for the program ahead?
So we're in the design phase for the final production aircraft as well. So that's going on in parallel to our flight test activity at the moment. After transition, we're looking to do public demonstration flying, and then recently we've announced a hybrid variant of VX4 as well. And so it's been mentioned a few times. We've got really high grid to shaft efficiency with the battery electric aircraft, but perhaps not the range. So that hybrid solution is perhaps the key to unlocking greater payload, greater range for markets like cargo or defence, where you can have a hybrid complement to the battery to provide your cruise power that's sized to meet the cruise power, but then with the batteries to help with the heavy lifting, literal heavy lifting, for takeoff and landing as well, if you want to do a vertical takeoff and landing. So we're really excited about that. It's something our customers, people we speak to externally, are really excited at too. They can see application of the hybrid aircraft in lots of other markets as well, not just for the shorter range passenger transfer applications we've discussed already.
Yeah, absolutely. Yeah, there's many different options that you could take forward, I'm sure. So that's great. Okay, we've got some other questions coming through. So one of them is around fuel cells. So probably Dave or Tom, maybe. Somebody is interested in the current fuel cell work that we're funding in the ATI. What's the balance between low temperature and high temperature fuel cells, and how do we see that funding changing over the next decade? So who'd like to take that one?
Just start, and Dave can chip in as well. So it's a really good question. I think quite a timely one as well, because there's pros and cons with both. They're in different stages of development. The LT PEM and the high temperature solutions. Both are in the program. We're looking at them both really carefully. The high temp solutions are obviously they ease some of the thermal management challenges because you've got a bigger temperature differential to play with. But I think one of the things we can flag, which is hot off the press, is that we've just announced we're funding Intelligent Energy with their Heights program, which is looking to adapt, use advanced thermal management to get some of the benefits of LT PEM with, by essentially adapting or managing the DT. From a radiator perspective. So some quite clever solutions being developed in the program to try and manage the pros and cons at the moment. And I suppose generally speaking, we're looking to support, like any technology where the roadmap isn't completely clear yet, and there's risks and pros and cons in both. We'll support them to the point where there's a clearly preferred solution or architecture coming through.
Excellent, thank you.
Just to sort of add to that briefly, at the moment, what we're seeing is that, as Tom said, going to high temperature fuel cells gives you a benefit from some of the thermal management, but they're looking like they're slightly lower efficiency than low temperature at the moment. So one of the questions we're assessing is, how does that feed into the overall aircraft design? Where's the optimum balance? And as we continue to study that, I think that's what's going to guide where we continue the research in the next 5 or 10 years.
Yeah, absolutely. I'm going to take another question now. Thanks, guys. Another one for Simon, actually. There's a question on when do we expect the next prototype to fly, and who will be at the controls? Might you be at the controls of that one as well?
Quite possibly. So we've got our third prototype aircraft. So aircraft 1 was built in 2021-22 timescale with ATI funding. I have to say, we wouldn't be here without that. Aircraft 2 is the aircraft that was flown. Aircraft 1 was flown almost entirely remotely, mostly with automotive suppliers. Aircraft 2 is our current test aircraft. Again, higher pedigree, got much greater involvement from our aerospace suppliers. So it looks and feels much more like a polished aerospace vehicle. And imaginatively titled Aircraft 3 is in build at Kemble at the moment. So we hope to see that out later this year. It might be me. It could also be Paul Stone, who did his first flight in Aircraft 2 last week. Paul Stone, ex of the Royal Navy, Sea Harrier pilot, and BAE Systems, and from Volocopter, one of our German competitors. Okay. Or Tim Eldridge, who's a rotary wing test pilot. He might make his maiden flight on Aircraft 3, but coming soon.
That's fantastic stuff. And there was a technical question around the downwash or outwash of the VX4. I mean, have there been sort of test measurements and things or assessments of that yet? And how's that looking?
Yeah, we've done some downwash characterization, relatively limited in its early days. So I'm aware there's a UKCA paper, Richard Brown paper on the potential risks of sort of high velocity jets and things. Our practical experience is that it's quite an easy aircraft to accommodate. It's a thing that's been considered for design for VX4. More research to come.
Okay, there's we've got a little bit more time for questions still, so I'll carry on. There's a couple around future fleet growth. I guess this is perhaps aiming at, you know, there's a big demand for aircraft. So is it time to legislate minimum passenger seat density? I don't know. Dave, do you want to take that one? Whether that's something in our market modelling we've been looking at?
Yeah, thanks, Jackie. Well, we look at this in two ways. When we're doing conceptual aircraft design, we fix a cabin configuration because you have to make sure that that's common across different aircraft, because otherwise you're not doing an apples to apples comparison. In reality, the cabin configurations are driven by the market and by the airlines themselves. And that's why you tend to see different airlines making different choices, whether they have a 2-class layout or 3-class or single class. I don't see the UK legislating on that in future because it's already a point of competition. It's one of the reasons that flying on low-cost carriers is the least carbon intense of all the airlines because they have that seat density. So I think the airlines will continue to focus on that, but there is a balance to strike between efficiency and passenger comfort. As somebody that's quite tall, I can't say I enjoy flying if my knees are jammed into the seat in front of me.
Okay. There's also a question, might be a tricky one for us to answer, but we can try and have a go. How does existing government legislation play a part in driving hydrogen-powered aircraft market? And what changes or incentives do you see as necessary to drive rapid development and adoption? I mean, I might go to Dave on this one again, because as part of the task force activities for zero carbon, do you have a view on that?
Yes, so I'm currently chairing a group with the Jet Zero Task Force looking at hydrogen aircraft on behalf of the UK government. So currently there isn't any legislation on hydrogen aircraft, and frankly, I don't expect there to be. I think the general approach the UK takes to this kind of thing is that it has to be market driven. And that's what we see in terms of the airline's view. We have to find a way to make things that are sustainable, economically competitive. There have been some moves in the SAF space to introduce mandates, but I don't expect to see that necessarily in the hydrogen space, at least at the aircraft level. There may be some things around the production, but that's really a separate conversation. In terms of driving development and adoption, well, the development is part of the reason the ATI exists, to provide the funding to help progress the research, development, and technology at pace. So that is a key part of what we're here to do. And we've recently been given a 10-year funding agreement in the industrial strategy. And so that gives players in the industry certainty that they can put forward new ideas for projects with time to develop those into the future. So I think the ATI has a huge role to play in that and help make the business case where there could be market uncertainty rather than driving it directly through legislation.
Yeah, I think that leads on to a question as well around hydrogen, and obviously it being very nascent, if you like, for aerospace, and a slight challenge maybe on, were we too quick to move to push hydrogen as a potential propulsion system of the future, given that there's been some slow back on projects coming from the likes of Airbus recently, as it's in the public domain. Tom, do you have a comment on that, perhaps?
Yeah, thanks, Jackie. I think it's really important to for us to say that we've got an independent technical capability that's underpinned by projects like FlyZero that have gone in the past, and they concluded that hydrogen was an extremely attractive fuel for aircraft use on a range of scales, as Dave said earlier. we've been discussing this quite extensively with some of our international peers, and the interesting thing is that many of them have also been running their own studies and are coming to those conclusions as well. So technologically, we're looking at the work that is underway, and there are no showstoppers. There's certainly some big challenges, but there's no showstoppers been identified. And what we've been trying to do is convene industry at the moment to say, how do we maintain momentum on this? Because the issues that keep coming to the fore are clearly focus on trying to get current parts out into the supply chain for current fleet and get ready for single aisle. But what we're trying to make sure at ATI is to maintain a balance of activity, you know, with a view to 2050 and beyond as well, where we expect hydrogen to have a significant role. The issue at the moment is just the appetite for investment in it. So we're looking at a range of initiatives to try and maintain momentum. But the critical thing is that the technical merit of it, objectively with our assessment and those of others that we review too, are that the direction of travel is correct. You know, we'll keep looking at that, but you know, we want to keep supporting its development, and we'll look at means to do so.
Yeah, I was going to sort of turn the question very slightly to Simon on the electrical side of things as well. You know, how important is it for these very new technologies to have that sort of government or public research and development funding to help move them forward?
Yeah, there's two things there. I think firstly, yes, that seed corn is really important, both to practically help and to show governmental support and commitment for the development of these technologies. I think the whole ecosystem's growing. If you look at how aviation began at the start of the 20th century, you know, we went from Louis Blériot's Blériot 11 crossing the Channel in 1910-ish to having a comet in the 40s. So in less than 40 years, we went from a fairly shocking first flight across the Channel that nobody could quite believe to jet airliners and intercontinental travel. I see this whole system will develop. So even though, say, you know, battery electric, relatively short range air taxis, people might say, well, how's that applicable to getting me to New York City on business travel? Well, I think the answer is you start to build the ecosystem. You develop the technologies to incorporate electric propulsion, regardless of the power source, into aerospace products. How to certify motors, powertrains, power systems, and it grows from there. So we're at the start of a long, fascinating journey. And then the ATI support at Vertical, I think David captured it really nicely. It was funding for aircraft one, and then we're ironically not a vertically integrated aerospace company. We partner strategically with people like Leonardo, Honeywell, but then batteries and propellers are the things we're doing in-house, and both of those programs have been supported by ATI projects that are still going today. So hugely important.
Yeah, fantastic. Okay, and I think we are timed out on the Q&A now, so I'm going to have to bring it to a close and thank everybody that's joined me in this Q&A, and thanks Simon again for the questions earlier as well. And that's going to bring the webinar itself to a close. I just wanted to say that I hope this has given you a snapshot of the many opportunities for technology evolution and revolution to really have a strong sustainability impact for future flight, and shown you that the UK is at the front, you know, it's really front and centre in these exciting future developments. So that's fantastic. Just to say as well, there are lots more opportunities to engage with the ATI, including registering for our mailing list, joining our events, and of course, engaging directly with us with your ideas for the 3 funding programmes that we run. And in the meantime, you can find out more about the ATI on our website, ati.org.uk. With regards to this Net Zero Week, there are more live webinars available. So please do take a look at the full agenda of events at netzeroweek.com. And I'll just say thank you very much for joining us, and we hope to see you again very soon. And goodbye.